Thank you for the introduction. I'm very pleased to be here, and so the talk is something like 40-ish minutes long, so not too long. So please jump in and interrupt me if you have questions and clarifications needed. Okay. Okay, and so I'd like to begin today by just giving you a quick overview of the work I've been doing through my PhD and postdoc, to give you a glimpse of my interests and hopefully spark yours. So as Kieran mentioned, I did my PhD at IPhT-TV with Olivier and Raphaël Voiturier, and we have been mostly focusing on understanding fundamental properties of some microscopic single particle models that are relevant to physical and chemical modeling. And so broadly, my PhD has been going into two directions. And so the first part of my work with Olivier and Raphael has been trying to characterize the geometry of the exploration by lattice random walks in confining environments before escaping that environment. So specifically, what we've been trying to characterize is for a random walk inside a confining lattice geometry, how many distinct sites, which proxy for the territory, are visited before the exit site, which is located somewhere inside the domain, is reached by the random walk. And so typically, these can be meaningful models for minimal, spatially limited reaction models. So if you have some reactants, if you have some reactants here in purple inside your domain, for instance.
Il y a un bâton.
Il y a une grande baguette à l'ancienne.
Non, mais le doigt, c'est...
Il était dans un moiton.
Le doigt, ça va.
Parce que le truc mais électronique, là, il marche pas.
Il marche, mais c'est juste que je le vois pas.
Après, ça fait un gros truc vert, enfin, je sais pas où.
Mais c'est ton PC. Là, tu es sur ton ordinateur.
Ah oui.
Dans le sport du software.
Moi, ça me va avec le doigt, ça vous va.
Nous, ça nous va aussi.
Ok. So if you have some reactants inside the domain, so here in purple, typically the number of distinct sites visited is a good proxy for your chance of reaction with the reactants. And what we've been trying to do is uncover universal behavior of the statistics of this explored territory, and typically extract information on how it would depend on the confining structure, its shape, its spatial dimension, its fractal dimension if possible, etc. And so the second part of my PhD work has been less focused on one single observable, but more on a single type of stochastic process that maybe now is ill-defined, but we call them jump processes at the time, which are simple discrete time random walks, which have continuous increments. So here in purple, for instance. And these guys would be typically well suited to describe empirical time series, so maybe single particle tracking data or protein backbone conformational data. And the point we're trying to make here is that because time series are discrete but describe an underlying continuous model, there's discrepancy between the two. And what we've been trying to do is reconcile these discrepancies between discrete dynamics and continuous models, specifically in the case of first passage observables, which I'll discuss a bit later on. Okay, and then as I transition from the PhD to the postdoc, I guess I try to shift towards modeling of more complex or at least multi-particle systems, where I can use statistical tools I've learned through my PhD, but also conjugate them with modern numerical methods stemming from the machine learning literature and try to uncover interesting dynamical behavior. So I went to Stanford with Brent Rotzkopf to do that, and we have been focusing on two subjects so far. So our first point of focus has been understanding and building minimally dissipative controllers in stochastic thermodynamics. So roughly speaking, stochastic thermodynamics is a framework to understand energy, work, and heat dissipation at the level of single stochastic trajectories. And one of the most natural questions in that context is how can we drive a system from some initial state to a final state in a finite time? And you want to do that by minimizing the associated heat dissipated along the trajectory. And so by now, this is somewhat of a standard question, but it's kind of hard to build and realize optimal controllers that actually take a system and drive it from A to B. And so what we've been doing is using machine learning tools to actually realize these optimal controllers and try to control the associated dissipation. And then the second topic we've been looking at falls into the realm of response theory, so specifically understanding how dynamical systems react to perturbations. And so in the equilibrium case, we have typically the fluctuation dissipation theorem that tells you how you respond, but these do not hold out of equilibrium. And briefly, what we've been doing is trying to build response estimators for general dynamics, specifically in the case where the diffusion tensor of dynamics is modified, and we'll talk more about that as well in the following. Okay, so I guess what I'd like to convey with this, kind of introduction here is that what I like to do is stochastic analysis for dynamics, generally speaking, either in the minimal setup, but also in the more general, higher dimensional PDE framework, where I like to understand dynamics and can also employ modern numerical methods to do that. And so I won't talk about all of this today, it'll be a bit long, but I'll just focus and divide the talk in two parts. So some PhD work, which I'm happy to present, which is nice, and some more recent postdoc work that I've been doing this past year. Okay. So without further ado, let's jump in this first part. So, okay, first off, what do I mean when I say that continuous modeling is not enough or not sufficient to capture discrete statistics? Well, first of all, discrete dynamics naturally arise in physical data. So maybe you have some intrinsically discrete behavior because you're looking at bacterial motion. We have heard a lot about the E. coli run and tumble type motion, but you can also have scattering type events, which have continuous bipolar trajectories. But maybe more importantly, as I've mentioned, we have discreteness in the data arising from limited time resolution of your measurement device. So when you're tracking a particle, you can't have its position at every single time just because you have limited time resolution. And so you have discrete data arising, and this can have, say, not dire, but big consequences on the statistics of first passage observables. So specifically, the thing I have in mind, we can exemplify it a bit more. So we have a particle evolving here in black. It has some continuous dynamics. It could be a Brownian particle, for instance. And we measure its position at discrete time steps, just because that's the time resolution we're allowed with our measurement device. And one is interested, say, in the residence time inside that red blob here. And you'd like to know the statistics of that residence time, just because it's interesting to quantify some physical phenomena, for instance. And so you have a continuous model for that, which would predict the mean residence time as a function of the size of the blob, and that would give you maybe that red line here. But when you do your empirical measurements of that mean residence time, you get a discrepancy because of that finite sampling or observation timescale you have. And so if you want to properly reconcile these two here, and you can't have the purple dots collapse on the red one just because you don't have infinitely precise measurements, it might be a good idea to focus directly on discrete dynamics and less on continuous type dynamics. So that's, I guess, the name of the game. And so, a nice way to go in that direction is to choose another type of modeling, which is not continuous. And we'll start with one dimension, but more as a, say, stepping stone for a higher dimension later on. And so the model I've been focusing on are these jump processes, which are essentially just single discrete time random walks. So we have in 1D a particle on a line, and it starts from some initial position x0 here, and the dynamics are fairly simple. You have just position at time n plus 1. It's just that at time n plus xi n, but all the xi n's are IID random variable, which share a common distribution f of n. So,
what is that?
The length of the jump. on 1D. Yeah. And so for the work at hand here, we won't impose so many restrictions on f of L. We just want it to be continuous and symmetric. So that's the framework we'll be working in. And so specifically to describe this f of L, there's a variety of f of L one can choose, exponential, and Gaussian, etc. But for us, we will only characterize them via the large L behavior, so the tails of the distribution, which are also characterized by the small Fourier expansion of the Jump distribution, which gives us the important information on the behavior of the tails of the distribution. So maybe the two important things here are the mu, which is the Levy index, which tells us how wide the tail of the distribution are. So mu can range from 0 to 2, and if mu is equal to 2, we have typically a variance, and if mu is smaller than 2, we have potential, well, we have diverging second moment and potentially diverging first moment. And a mu here is just a length scale to scale the Fourier parameter. So essentially, we'll just consider f of L's, which are characterized by their large tail behavior. And the Levy index is also important because it characterizes the long time behavior of your walk. So if you let it evolve for a bit, it starts looking like something else, which is described by this mu index here. Okay, so of course, we're not the first to look at these jump processes or random walks here. They've been around for a long time. And one asks about the statistics of these random walks. And there's already a bunch of very many results in the literature corresponding to that. So specifically, one might be interested in the statistics of the particle position after a large number of steps, or actually any number of steps, right? And both in the infinite case, where the particle can evolve freely on the whole space, and in the case that we deem semi-infinite, where there's a barrier here at 0, and the particle is absorbed or killed upon crossing 0. In both these cases, the distribution of the position after n steps is known analytically for any continuous symmetric jump distribution. What I mean analytically, at least in Fourier transform space, but that's enough for asymptotic analysis, at least. And there's also a number of results in this infinite and semi-infinite cases concerning the asymptotic behavior of the random walk. So essentially, all central limit theorems and functional central limit theorems describe what it looks like when you look at it after a long time and from a large distance. And so I guess here this sort of leaves a hole which corresponds to these random walks that are confined in some finite interval 0x. So if we now have two absorbing barriers here, 0 and say x around here, we'd like to know, are there any universal results concerning the statistics of these random walks for arbitrary continuous symmetric f of L that we can extract and have apply for any jump distribution. And it doesn't seem like there is as such a general result as there could be for semi-infinite or free jump processes.
Sorry, Shani. When you say confined, it means that if your jump goes out, you just don't take it.
No, it means you stop the walk, and so the statistics you consider are conditioned on staying inside.
Okay, so it means, is it not the same? If you're somewhere and you want to make a jump which is going out, you just don't take it.
But
no?
Well,
you stop it at the boundary. What do you do? If you consider an n-step long walk, you only take the positions that are inside the interval. If that makes sense. You do not allow for any jump that would be outside the interval, strictly outside. Yeah. I mean, it could be equivalent to not taking it and redrawing if you forget that step, but it's to be discussed. Okay, yeah, it's not
okay. And so, and in that context, I guess we don't have the pretension to exactly characterize the propagator, just because even for continuous models, we know it's very hard to do. But we can still look at some first passage observables, and typically the one we've been interested in is the so-called splitting priority. So, as Karen mentioned, we take jumps inside that interval, and at some point, the particle is going to take one jump outside. And this is when we stop the process and we ask, are we on the right-hand side or are we on the left-hand side? And so typically this gives you the probability of escaping the interval to the right or to the left here. So what we're asking is, can we characterize this splitting probability here, which we did not pi, from any initial position x0 inside the interval, 0 and x included, to cross x before 0, and just to motivate a bit that study. I guess the splitting probabilities are fairly important across disciplines. So in the financial realm, it tells you the probability of going bankrupt, I guess, or reaching a certain threshold. From a population dynamics point of view, this could describe extinction probabilities of alleles, so having one allele die to the favor of another one. And in the chemical context, which is what I've been more exposed to recently, these splitting probabilities are perfect reaction coordinates to tell you how far you are from some reactant or a product state, if you just monitor in some distance. So what we're interested in is characterizing these splitting probabilities for Judd processes, random walks, for arbitrary Judd distribution f of a. And specifically, what we'd like to know is, are there specific discrete effects that you get by looking at random walks instead of looking at bounded motion, for instance? And in this case here, we have some non-trivial behavior when we start close to one of the boundaries. So essentially, even if you start at 0, you have a strictly non-zero probability of crossing x before 0, because any rightward jump will bring you either back into the interval or over x. So that's this quantity here, which typically would be 0 for bounded motion, is strictly non-zero when you add in this discreteness, and that's something we'd like to characterize as generally as possible. Okay, so a way to do that would be to try to solve exactly for pi here, so try to compute it exactly for any value of the starting position x0, but this is somewhat not doable because the splitting probabilities solve integral equations and not ODEs, and for arbitrary Judd distribution, there is no real chance of getting any analytical exact results for the splitting probability. But we can still try to extract some relevant information, and typically one is tempted to look at the large interval limit. So we now have x going big, going to infinity, and we're trying to characterize the behavior of the splitting probability in that asymptotic limit. But what we want to do is be able to obtain a result that safeguards the discrete nature of the process, in the sense that even as x is big, we want that thing here to be non-zero. So we still want to be able to observe that there is a discrete effect. So we're looking at trying to characterize the splitting probability for any x0 in the large x limit. And so this is what we did, and I'll just go with the results. So essentially, what we found is that we have a universal asymptotic behavior of this quantity here, the splitting probability, for any x0. And here I'm just showing it for x0 equals 0, just because it's fairly simple and a nice result. So essentially, we see that it doesn't depend on much. It depends on, well, the size of the interval x, the length scale, just because we want this to be without dimension. And then we have an algebraic decay, which is characterized or indexed by the Levy index mu. So this is a very general formula, which is nice, which tells you if you have a random walk starting from 0, send your interval to infinity, this is how the splitting probability will behave, and you can measure it as you follow your dynamics.
So what is the exponent for
On the right?
This one? Mu over 2. This mu being the mu of the... Okay, actually there's a title here. Okay. If you're familiar with the bounded motion type results, mu is equal to 2, and we get 1 over x, or x0 over x. So there's no agreement, which is expected but nice. Okay, and so conversely, one could argue that this result being simple enough, if you don't have access to the dynamics of the single jumps, just because you can't measure them, maybe this quantity is more of a macroscopic type observable that can measure over a lot of realization, and you could infer or extract the relevant parameters mu and a mu that describe the tails of your giant distribution that might not be accessible otherwise. Okay, and so what we did is just conduct numerical confirmation over a range of different jump processes with narrow tails, heavy tails. Anyway, what happens is that we get agreement as expected, which is nice. But maybe more importantly, we realized that this quantity, the splitting priority, is relevant in some experimental settings. So specifically, we've been looking at the works of the De Silence et al. Group that they have been conducting over the three or four last years, where they measure transmission priorities of scattering photons in heterogeneous media. So essentially, I don't know about the details, but what they do is they have this slab type system with a vapor inside. They shine a beam of photons here, and they measure the outcoming intensity, or the ratio of this intensity through H2 rather than through H1. So essentially, how many of the photons, if that makes sense, escape through H2 rather than through H1. And even from the picture, you can see that this process is controlled by a splitting priority of an effective 1D process in that direction. So essentially, what they measure here, these transmission priorities, which they observe do decay algebraically with the correct exponent, is akin to an effective splitting priority from 0, since the photons start on that slab H1 here. And so there's potential that we could do quantitative comparison with the theoretical results here. Okay, and that put aside, maybe I think what I want to come to here is that, as I sort of hinted at the beginning, this is a 1D quantity here, but we see that it's somewhat relevant to higher dimensional problems. So here this is a 3D one, but it's effectively 1D, right? And one could ask, is there a way to extend this to higher dimensional jump processes and more general first passage observables that are not only the splitting priority? So this is what we try to tackle next.
Jérémie?
Oui.
What is the origin here of the Levy law for the photons? Do you have any idea? What is the index and why is it Levy?
So the index, I believe, is 1/2, if I'm not mistaken, from what I recall from the experiments.
Is there any relation with these experiments of the LKB group and the Bouchot's work?
No, I don't think so.
Okay.
But I
So
think
where does Levy come from here?
so. The Levy behavior comes from the way they describe the scattering process of the photons as they collide with atoms in the hot vapor, and they have a broadening of the scattering distribution, from what I understand, which gives some. In the Bouchot work on glasses, for instance, where you have the trapping type model, where you get Levy by weighting, and there's a depth, and you have to convolute two distributions, you get Levy. This is the same type of math they do to describe the Levy type index of the scattering, and they just actually, in the experiments, they first conducted the transmission priority type experiments, measured the algebraic law, which was not 1, so they decided it should not be with the variance type jumps. And then they had another type of experiments where they tried to isolate the single jump and show that they got this mu equals 1/2 type of exponent.
Is there not a simple physical explanation of why it's not Brownian?
Not that I would know of. And not that I recall reading in the manuscript.
Sorry, the medium is what?
The type of element.
Yeah. What is the medium?
It's a hot vapor, but I can't tell you which elements.
So they found x to the 1/x to the power 1/4. I mean that's the result of the experiment.
Yeah, what they vary is the width, and they did find 1/x, but the 1 is arbitrary, right? Because they found the power law with the 1/4. Yeah.
They were okay. Let's see.
With strange why?
No, I mean, why 1/4?
Well, I mean, typically, if they got 1/4 and then they did the single jump measurement and they got a half for the, so if they got a half, typically they would have, diverging first moment for the mu. No, the relationship is consistent between their two experiments and between, but this is not specifically discrete, right? If you do, for instance, if you do continuous modeling, so Levy processes, you also get that relationship between the splitting priority and the instantaneous distribution.
1/4 sometimes is Brownian over Brownian. I mean, there are some kind of idea like that.
So, okay, I see what you're referring to, but I don't believe that to be the mechanism they identified. Any other questions? Oh, okay. So what we set out to do next is, maybe take a slightly more general approach, and we considered the same discrete time random walks with continuous increments in higher dimensions, so typically 2 or 3, and we put them in, some confining domain here, which is a 2D1 for the example, with a boundary sigma, and we let the system evolve. And the question we ask is typically, what is the mean exit time for these processes? Where do the processes exit when they cross for the first time the boundary? What portion of the domain is explored before the walk escapes the boundary? And so typically all these are just called first passage observables in the sense that they're anything you can evaluate or compute whenever your random walk exits for the first time. And the splitting priority is 1. In 1D, it's you escape either left or right, and you ask, where am I? So it's a special 1D instance of these first passage observables. And again, the question we've asked is, in the large confining domain limit, independent of its shape, just take it big with respect to the length scale of the random walk jump distribution, is there a way that we can describe the universal behavior of these first passage observables for discrete random walks that capture the discrete effects, in the sense that if my random walk here starts from the edge of the domain, it's strictly non-vanishing because any jump that brings me inside here resets the random walk process. So we don't want all these quantities to be vanishing as x0 goes on the boundary. We want to maintain the fact that we have discrete steps. And so to answer the question, what we've done is have a bit of a matching or boundary layer type argument where for arbitrary first passage observable B, that could be first exit time, position upon exit, etc., we can relate it to the same observable for the continuous limit that we described. So think of mu equals 2 and the continuous limit being the Brownian motion. So we can express these statistics of the discrete walk in terms of the statistics of the continuous limit, which are assumed to be known. There's no cheating here. We're not claiming to derive any novel result on the right-hand side here. We assume it to be known, times a quantity, here this pi h1, h2, that someone characterizes the propensity of our walk to penetrate the bulk of the system. And this quantity here, in fact, is an effective one-dimensional quantity, very similar, or actually exactly equal to the one we just discussed beforehand in the three-dimensional setting. So it's a splitting priority of going inside the domain, and it's 1D because we can just model it with hyperplanes, close to the boundary where the walk stops. So in essence, if we assume known the continuous limits, that thing can be extracted from data, and we have expressions for the discrete versions of the statistics of these first passage observables, which is what we're aiming for.
Sorry, do you have a well-defined hyperplane if the dx0 is something, is a region, a sub-region of sigma? When you take a point, it's okay, but if you take a region, you don't have a tangent hyperplane.
Yeah, so you're right, there's also the case if the boundary is rough or too rough, there's no way we can define an hyperplane. So there is a lot of approximations here. We need to be able to define these hyperplanes. We need the system to be fairly big with respect to the size of the hyperplanes A, so it's the double limit, and
one could always construct cases where this fails, for sure. So yeah. Well, assuming, if we zoom in, the surface is smooth enough that we can have it with the hyperplane. Thing is big enough that we can insert the hyperplane to be also big, so we can evaluate that thing in the asymptotic limit, then it somewhat works. And so just as an illustration of cases where it works, we've been looking at these exponential type just distribution. Oh, that should be an F. So we have a two-dimensional process which takes exponentially long steps and then reorients and does it again. And we've been looking at geometric first passage observables. So in that case, we have a particle starting on the rim of a disk, and we want to know what's the probability of entering an inner inclusion here before escaping the disk. And what we do is straightforwardly apply this. So we compute the continuous limits, we compute this quantity pi here, and we have a no-fit agreement, which is demonstrating, I guess, the validity in that case of the matching relation. And that also works for dynamical type first passage observables. So here we have somewhat of the same setup where we have a disk, and we consider the distribution of the exit time, at least in the large size limit. And again, we have a no-fit matching, which is what we're looking for. Okay, that's about it for that part. So there's extensions to be at some point considered. So one of those I'm very interested in is we know that discrete measurements induce discrete dynamics, but they also induce memory in the dynamics. And here we've only been looking at strictly Markov models where we don't have any correlations in the increments xi. And so it'd be interesting to know if that sort of stuff works for correlated increments and limiting continuous processes, which numerically seems to work sometimes. So that's to be investigated. And then, of course, there's the case of space-dependent jump distributions, which corresponds to limit evolutions in a potential that I haven't looked at too much and would be interested to look at in the future, I guess. Okay, and that concludes that first part here. Yeah, okay. So any questions maybe, or, yeah?
Is the first passage that you use the same as in first passage percolation? Because you can visit here a site several times before exiting. But as first passage percolation, you will only visit the site once before percolating, right?
Yeah, so it's the first version. It's you can live arbitrarily long on any place in that domain. It doesn't. You're not constrained to go only once any place.
Is the terminology first passage standard in this case?
Yeah. Excuse me.
I'm not a physicist, so it's a question for physicists.
What's the question? Is the terminology first passage?
It is standard to call this first passage, even though you can visit the site several times before exiting.
Yes, it's first passage with respect to the outside or to the target, but the rest is independent of that.
It's, for instance, first passage in the same sense as the title of the book by Sidredner.
The blue book. Yeah. Okay. Okay. So I guess I'm on time. Yeah. Okay, so then I guess I'll just jump. So it's somewhat unrelated, but I did want to talk to you about two different things. And before talking about what I've been doing in this context of out-of-equilibrium diffusion sensitivities, I just like to frame the discussion in the general context of dynamical analysis from molecular dynamics, which is what I've been exposed to recently. So, namely, what one wants to do, we're looking now at more complex systems. And we want to be able to extract some dynamical information from molecular dynamics of more complex systems. So typically, which region of phase space are visited, in which order, and on which timescales, which is relevant for chemically oriented questions. And so, briefly, if we could do everything, we would just take our system and then run maybe ab initio chemical computations or use force fields to run the dynamics and extract dynamical information from the time series, but that might be too expensive from a computational point of view
for bigger systems. So a way to bypass, or at least alleviate that difficulty, is to coarse grain out part of the system and describe the relevant degrees of freedom in terms of generalized Langevin equations. So now we're back into the Langevin realm, but we have a memory kernel that describes the interaction with the degrees of freedom that have been coarse grained out. And this is cheaper from a computational point of view, but not that nice from an analytical point of view, because it's harder to deal with the memory kernels and the non-Markovian effects. And so we just go one step further and we forget about the memory, and we describe these dynamical systems in terms of underdamped or overdamped Langevin equations, which don't have any memory kernels and memory effects, and are purely Markovian. So that's more of the context that we're in now. So we left the discrete space and are now in continuous space. And essentially anything that we'll be discussing is described by a Langevin stochastic differential equation. And to make things clear, xt is any remaining relevant degrees of freedom. So that's a vector. That's just the equation of motion, right? B are all the forces that act on your system. So maybe a forcing field or some Lennard-Jones potential type of stuff. And then the diffusion tensor here, so that's a drift. And the diffusion tensor describes your interaction with the thermal bath that has been coarse grained out as well. And so typically that would be your temperature. And dWt is the standard white noise. And so this is a very simplified description of this original complex system here, but we still expect it to yield some relevant information, maybe on relaxation properties, reaction rates, and reaction pathways, so how the system evolves between the different states of the. But what matters for us here is to know if from that sort of formulation, we can extract some response information on your system. So essentially, as we change slightly, so in the linear regime, either the drift, so maybe we tweak the intensity of the Lennard-Jones potential, or maybe we ramp up the temperature somehow. We want to understand how the system described by such dynamics responds to perturbations, and if we can typically quantify this response without having to perturb the system. So in the equilibrium case, for which the equation of motions, or at least the drift, is just a gradient of a potential, we know that we have the Boltzmann distribution here for the stationary distribution, and the answer has been known for quite a bit. So the fluctuation dissipation theorem relates the response to perturbations, typically in the parameters, or as we add a small potential to this U0 here, or as we tweak the temperature by increasing it a bit, for instance. So it relates the response to these perturbations to the fluctuations of the system unperturbed. So specifically in that case, A being any generic observable that describes the structural properties of your system, so it may be radial distribution function or any other parameter that you're used to working with. The response to a perturbation, here I chose the temperature, is just related to the fluctuations of correlation functions, well, at least the correlation functions in the unperturbed system of your observable interest A times here the energy function. So essentially, if we want to measure that response, we just look at these fluctuations, which is nice in the sense that we don't have to perturb the system to extract the response properties. And so now one asks, if we have a non-equilibrium system, so typically we have some non-conservative forces acting on it, are there equivalents to these fluctuation dissipation terms? So there are some, but today I want to talk about another one. And just to fix ideas, maybe the system we have in mind is an interacting particle system, which has, these are trendy, some active components, some self-propelling components, which cannot be described as the gradient of some energy. So in this non-equilibrium case, maybe we have a non-equilibrium steady state, and we want to characterize the response of the steady state to a perturbation, or maybe we don't even have a steady state, we just have a dynamically driven system, and again, we want to characterize the response to a perturbation, either in the drift, so adding, say, a non-conservative forces, or in the diffusion tensor, which here is taken to be the temperature, but could be anything, right? Okay, so I'll start with the drift case. So this is known results, but it's nice to present them. So we have a unperturbed drift, and we add a perturbation. and the diffusion tensor is unperturbed, and we ask how the system responds. So this has been, throughout the literature, explored in different directions, either the, as we mentioned, actually, the financial realm, molecular dynamical simulations, or stochastic thermodynamics. But essentially, all of this revolves around the Gersdorf transform for SDEs. So I'm sure a lot of you know it better than me, but I'll just go through it. So the Gersdorf theorem is just a change of measure type relation, as you would do for importance sampling, for instance, to relate the expectation of any observable A that you care about under the perturbed dynamics, so with this B tilde field here, to the expectation without, so the unperturbed expectation of the same observable times another stochastic weight that you have to track as you run your SDE. So there's conditions for that to hold, but we'll just assume they hold. And what we're interested in is the response, so the properties for small perturbation B tilde here. And so we just carry out a small epsilon expansion of this. And what we obtain is a drift sensitivity, so a response to a perturbation in the drift. That's the perturbed case. As we change epsilon here, we get the expectation of the observable of interest times a weight that has to be tracked along the dynamics. And here in this way, everything is known. And B tilde is the perturbation, so you know its shape. Sigma is the diffusion tensor, and DW is the white noise you inject as you run your simulation or as you observe a system evolving. And in this case, there is no real assumptions on the stationarity or the dynamically driven character of your dynamics. This just holds. So in a sense, it's general out of equilibrium and on the fly, because you compute, as you run the dynamics, you compute that bit incrementally. So this is very nice. But one of the critical limitations of the Gersdorf theorem is that it can only relate SDE dynamics between SDEs that share the same diffusion tensor. And so typically the question that we answer with the fluctuation dissipation theorem right before, and that we want to answer more generically, is what if we vary sigma? So what if we perturb sigma? This can't be applied as straightforwardly, and we'd like to obtain another diffusion sensitivity estimator. Okay, so specifically now we have a fixed drift, so that won't change, and then we have a diffusion tensor that we perturb with a small sigma tilde here. So that's our diffusion perturbed SDE. And typically that would arise if we have a non-equilibrium steady state and we have a global shift in the temperature, which is, I don't know, modify the temperature for a bit. But we could also have spatially dependent diffusion tensors. So the heated rod case could be a good model. Hot and cold. Yeah, hot and cold. And in that case, we want to know how can we write a relation of that type to take into account a perturbation in the diffusion tensor. And so what we've done is just to introduce another dynamics, which we call core shifted. So now we consider these dynamics here, which have a non-perturbed diffusion tensor and have a perturbation that has been somewhat inputted into the drift. So essentially, if we write it that way, and I'll come back to this in a second, we have a perturbation in the drift and not in the diffusion tensor. And if we use the PDE formulation of both these dynamics, so the evolution of the instantaneous distributions, what we see is that to first order in epsilon the perturbation, the distributions are equivalent. So essentially, if we compute any expectation of your observable of interest under these dynamics or under these dynamics here, you get to first order in epsilon the same value, which is what you want, since we're only looking at small epsilon expansions here. So doing that, now we kind of see that this one has a non-perturbed diffusion tensor, and so we're back to that point here, and we can just straightforwardly use the Gersdorf theorem to compute the response associated to that perturbation in the drift for the score-shifted stochastic differential equation. So what we obtain is a modified version of that one here, which also takes care of the perturbations in the diffusion. So somehow this one works also for perturbations right here. Okay, so that's sort of that result we obtain, which is okay. And so we just check it. So we can do some sanity checks. So we can do sanity checks on equilibrium systems. And that's, I guess, just a sanity check. So we check that it works. We can analytically check that it's equal to the fluctuation dissipation theorem, which is to be recovered. And then we did some numerical experiments on some equilibrium systems to compute perturbations of angular order parameters in these Lennard-Jones systems across more ordered or more diffuse phases, or at least behaviors, and compare with finite difference, fluctuation dissipation theorems, and our estimator, and we have good agreement. But that's just a check in a sense, and the method is more interesting in cases where we can't do any other way, right? And so that would typically be the case when the instantaneous distribution of the system is not known, either because it's a non-equilibrium steady state, or because it's just a dynamically driven system with an evolving distribution. So is our estimator useful in that case? Okay, so maybe we just take a moment here to look at it again. It's the same one, and so it involves the following functions. It involves the sigma tilde, which is the perturbation, which is an analytical form you know, the sigma, which you know also, which is the unperturbed diffusion tensor, and it has this function here, S, which is called the score of the instantaneous distribution. And so the score is the gradient of the log of the instantaneous distribution. So in an equilibrium case, the score would just be the gradient of the energy. But when you don't know rho t, a fortiori you don't know what S is. But what's nice for us here, so we need S to compute that thing. And what's nice is that the score is a function that has attracted a lot of interest in the machine learning community, in diffusion models in particular. And so there's no real restrictions in approximating that function using tools from that community. So essentially, if we have sufficient data, so sufficient snapshots of your unperturbed system, whether it be, I don't know, any computational snapshot of your dynamical system, the score is fairly well represented using neural networks or any other machine learning apparatus. So for us, what this says is that the quality of this estimator is only controlled by how well we can approximate that function S. And this is more of a standard machine learning exercise to do. So we can carry out, using these tools, the estimation of S and then the estimation of the response to a perturbation in the diffusion tensor. Okay, so as a proof of concept, this is more of a lower dimensional example, but we've been looking at active interacting particle pair on a ring. They have an interaction potential between the two. This is two-dimensional vector. And they have an active component, so it's typically out of equilibrium. And what we do is we just run the system, carry out the approximation procedure, evaluate the score, and then from there, evaluate the response to perturbations here in the temperature that dictates the dynamics of the system. And again, we have good agreements between finite difference schemes, which is what we want to avoid, and the estimator we put forth. So as proof of concept, it works decently well. And so I guess ending here, the natural next steps that one could bring forth is, this is a very low dimensional example, but in practice, dimensionality should not be too much of a problem because the approximations we use for the score are built for higher dimensional data from the machine learning point of view. And so it'd be interesting to go towards higher dimensional system and try to test the quality of the estimator and at least control it. And then another big limitation of this work here is the linear regime. So is there anything we could do to go beyond the linear response theory and looking at strongly forced systems on the diffusion tensor? Okay, and so I think I'm somewhat near the end. I have maybe 2 minutes, something. So I'll just highlight some of the things I'd be interested to look at in the near future. So as all of this work here has been focusing on Markovian evolution without memory, but I'd be interested in looking more broadly at these coarse grain dynamics in the sense of looking at generalized Langevin equations and extracting dynamical information from fine-grained simulation to these coarse-grained dynamics. So what I mean by that is that if we take one step back and relieve the assumption of no memory, typically the dynamics would be considering look something like that, with a memory kernel here that tells you how the past impacts your present. And there are cases, but generally speaking, there's no analytical formulas for what these kernels should look like, and they need to be parameterized for specific systems. So you need to make choices of what K looks like and try to infer the parameters of this parameterization. And so one of the limitations to do that is you have to run the complicated dynamics and the fine-grained dynamics for a long time to try to parameterize these kernels K here. But there's recent advances that actually allow us to easily go back and forth between a fine-grained configuration and a corresponding projected coarse-grained configuration. So in that way, it's always easy, but in that way, it might be harder. And there's actually recent techniques that allow to do that. You can train maps to do that. And so I'd be fairly interested from a practical point of view of trying to have nice parameterization of memory kernels, leveraging these numerical methods to get quicker and more precise estimates of what the coarse-grained dynamics should be like. And from a more theoretical point of view, there's also interesting questions which I guess I'd like to look at, which doesn't seem have been digged into too much. So continuing from response theory, one of the questions is, if we tweak something in the fine-grained dynamics, so if we change the temperature or the interaction, how does that reflect on that kernel here? Is there, for a given kernel, of course, for a given parameterized choice? So it'd be nice to be able to understand that. And then going into more of the interacting system realm, can we use density fluctuation approaches, or at least fluctuating hydrodynamics to describe that sort of systems, which I haven't seen done much, but would like to dive into at some point later on. Okay, and I think that's it. So thank you, and I hope you have questions.
Maybe I had a couple of questions. So you were able to shift the perturbation in the diffusion constant into a perturbation into the drift.
Yeah.
Can you explain? I mean, something like that happens, but I'm sure it's not the same. When you go from Ito to Stratonovich, you also have a kind of...
yes.
Probably it's not related here.
No,
what's the logic?
So if you have a Stratonovich description and you want to go into Ito description, that will add you a term in the drift.
Yeah.
But now if you have a Stratonovich description and you still try to perturb the associated diffusion tensor, as you go into Ito, you will get two perturbations. You will get that, and you will get an additional perturbation in the additional drift, plus one. So this is more of it's somewhat not related. It's a conventional thing.
Yes,
whereas here the way it works essentially it's not pas la question en français.
Ah oui, bah oui, on connaît, oui.
Pas très sorcier. Donc en gros, si j'écris ça, on peut écrire l'équation de Fokker-Planck associée, il n'y a pas de problème, en admettant que tout se passe bien. Et en fait, vu que la partie diffusion est linéaire, enfin pas tout à fait, elle est quadratique, mais du coup, à l'ordre 1 en epsilon, on peut passer la partie en epsilon, on peut l'envoyer dans le drift, et on a le terme epsilon grade sigma tilde rho, comme ça. Et en fait, du coup, quand on écrit Fokker-Planck sans enlever la partie diffusion, bon, en fait, je peux le faire au tableau. Si j'ai quelque chose comme ça.
Je vais enlever le terme B.
Ouais, je vais le garder juste pour quelque chose comme ça. J'écris celui-là. Quelque chose comme ça.
Ouais.
Et maintenant, si ici je fais plutôt... Alors ça va pas être homogène, mais c'est pas très grave. Si je fais quelque chose comme ça, là quand je vais là, ce terme-là, il prend un... comme ça. Et lui, je peux l'envoyer là. Il y a un Laplacien ici, pardon. Voilà. Et donc c'est pour ça qu'on récupère le score. Parce qu'en fait, on obtient B plus delta T sur T, score, grade log rho. Rho. Et du coup, il y a un autre. Donc là, comme ça a l'air de marcher très bien. Mais le seul point qui est un tout petit peu compliqué, c'est que du coup, ce rho-là, c'est pas le même rho que le rho où il n'y a pas ce terme-là. Mais c'est pas très grave parce que à l'ordre 1, ça marche quand même. En fait, si on fait la perturbation, c'est le bon, lui, c'est le bon rho. Voilà.
Mais en fait, on peut même dire d'une façon beaucoup plus générale que, en fait, disons, là, quand on fait un drive, on induit une distribution de probabilités. Et au premier ordre, le score que vous avez, c'est exactement le score. Pour induire cette distribution de probabilités, c'est exactement l'argument du modèle de diffusion que les gens en machine learning ils ont. C'est exactement ça, non?
Que le score, c'est le score pas perturbé?
Et, non, que la forme du score additionnel qu'il faut ajouter, c'est exactement la partie qui manque pour induire une distribution de probabilités.
Ah oui, c'est le bon. Oui, quand on va dans l'autre sens, c'est ça.
Ouais. Donc c'est le reste du modèle de diffusion.
Oui, tout à fait. Tout à fait. C'est pour ça qu'ils veulent le score.
Une autre question un peu plus vague, mais là tu fais de la perturbation sur ces processus stochastiques, tu essaies de trouver une sorte de fluctuation, réponse linéaire, mais autour d'un état, fluctuation-dissipation autour d'un état non thermodynamique. Il y a eu pas mal de papiers, tu sais, je sais pas si tu connais ces papiers de Kavetsky et Chetrit, où ils essaient d'établir un théorème comme ça de réponse linéaire loin de l'équilibre. Ça a un rapport avec ce que tu regardes. Je sais que c'est pas facile à lire, c'est assez formel, mais c'est des papiers qui sont assez...
Alors j'ai pas lu cela particulièrement. Pour autant, j'entends qu'il y a beaucoup de résultats similaires, mais de ce que j'ai l'impression qu'une des hypothèses prévalentes dans ces travaux, c'est celle de la local detail balance. Souvent, j'ai l'impression que c'est quelque chose qui est assez présent et qui permet d'exploiter le côté, comme disait Pierre Francesco, dans un sens, puis dans l'autre. On relie les deux sortes de dynamiques. Et donc, dans ce que Raphaël a fait, alors récemment, je ne sais pas, mais j'ai l'impression un petit peu plus avant, il y avait cette notion de c'est une hypothèse assez importante qui permet d'exploiter la relation entre ce qui se passe dans un sens et dans l'autre.
Et là, c'est pas le cas.
Là, j'ai tendance à dire que le retour n'est pas particulièrement pertinent. Voilà. Après, la littérature réponse-linéaire est vaste.
Donc
voilà.
C'est des papiers assez abstraits en fait, ces papiers avec Kavetsky.
Là, si je devais mettre, on va dire, en résumé rapide, peut-être le point important, c'est celui que, et d'ailleurs si on lit un peu les différentes reviews sur la réponse linéaire, en général ça s'arrête à on a une forme pour la fluctuation qui est formelle mais exacte et qui fait intervenir le ρT, la distribution stationnaire qu'on ne connaît pas, et donc la direction c'est approximer ρT, soit comme une gaussienne, soit comme uniforme, alors que là l'approche c'est plutôt, on n'a pas ρT mais le score, et du coup l'approche c'est l'approximation par l'apprentissage de la fonction. On sait qu'a priori on a des garanties pour que ça se passe plutôt bien dans la procédure.
Sinon, pas d'autres questions? Jérémie sera là dans l'après-midi. D'abord on va déjeuner ensemble, donc il faut les venir. Il sera là si vous voulez discuter un petit peu avec lui pour l'après-midi.
Merci.
Thank you very much.